we're going to step out a bit from experimental and theoretical thermodynamic for geochemistry in supercritical environment and just go a little bit more on how can we do geochemistry as an exploration tool for supercritical geothermal system. And this is part of some of the work that we're doing, as well with obviously some of the experimental work that Bruce and Peter are doing, and some of the modeling and thermodynamic modeling that Thomas and the team is doing. We're also working as part of this work stream under Geothermal the Next Generation with the University of Victoria and Wellington, the Victoria University of Wellington. And this talk is particularly it's a strong collaboration that I've been for years with volcanologist Colin Wilson. So without further ado, why doesn't it want to change? Sorry, I'm having an issue. Here we go. Well, the Taupo Volcanic Zone is what we are looking at in New Zealand. And this is to develop New Zealand supercritical resources, we need to understand this complex rifting arc that is the Taupo Volcanic Zone. It's a very active volcanic environment that created as much volume of rhyolite than Yellowstone in the last 2 million years. And if we are going to drill deeper, that also means we're going to drill closer to magma. So understanding the fundamental of what is the crust and the magmatic crust underneath the TVZ is really important for us to be able to understand where the magma sits, but what is the complex dynamic of the large hydrothermal system that are at the surface. So just to step a little bit more into a geological realm, which is my background, the Taupo Volcanic Zone is the on-land termination of the island arc, the Tonga Kermadec arc. And as you know, more recently, this arc is capable of doing very large volcanic eruption, as we've seen recently, unfortunately, in Tonga. And this Taupo Volcanic Zone is this extension of this back arc extension. And one thing that is pretty amazing about this location is the southern part of this arc, the termination basically of the volcanism, is your classic andesitic cone, and the north system as well, where you have White Island and the Kermadec arc, which are more traditionally andesitic magmatism. But the on-land part, the majority of what we call the central Taupo Volcanic Zone, is dominated by large rhyolite caldera-forming events and dome-building complex events, and that have been going on for at least 1.8 million years. This rhyolitic magmatism is associated with intense rifting, where you can have in the area here at the coast up to 15 millimeter per year of extension and 7 millimeter here. So it's not as well a homogeneous extension. You have a rotation of a North Island full system here. So you're basically opening that zone like a zipper, if you want. One of the interesting things when you start looking at where the geothermal systems are, and particularly the ones that have been utilized for electricity generation for the last 50, 60 years, even for Wairiki, if you are looking at where, and this is a great diagram that our colleague from Auckland, Julie Rowland, Mr. Simmons put together, where you're getting the highest heat flow, which is the histogram here, in distance to the Kangaroo Fall, which is basically correspond to the alignment of the arc. So this is your arc position. You're getting all of the high heat flux aligned with the arc around here. In between the two active caldera that are currently in the TVZ. So here you have one of the most recent supervolcanic eruption location on Earth, which was the formation of the Oronui caldera in the Taupo Volcanic Center here. and where Waiheke geothermal field is right here, Rotokawa, Oahu, and then you have the Okataina caldera here, which has been very active as well for the last 60,000 years, and except Waimangu here and Wotoiti that are located in the caldera margin. Most of the geothermal systems that have a high heat flux are located in that area along the arc front. So it's a little bit of background about the TVZ. So when we are thinking about what are the best targets to explore for supercritical resources, we kind of need to understand what are we going to look for and what kind of model, geological model, we are going to test. And one of the models that is important is understanding magma, is understanding if we're going to have a shallow intrusion or if we're going to have a large, deeper silicic mush that creates almost like a plate model, a unified heat source. We're also going to be tested for deep discontinuity. Remember, the Taupo Volcanic Zone is a very active rifting where we have deep-seated fault and discontinuity that are penetrating the crust and likely as deep as the zone of partial melt. So all of this needs to be better constrained. So what do we know about the magmatism in the Taupo Volcanic Zone? So if we're taking one of the most recent caldera events in the TVZ, this is the work from Finnegan Island Camp, Lake Camp, sorry, underneath Taupo Volcano. So we had, which is really right now what is happening. This is one that happened in 2018. So in our backyard. And what you can see is that underneath the caldera, which is where we know there is more or less magmatism, there is a zone of an aseismic zone. So they interpret, based on geophysical data, they interpret that this aseismic zone is likely linked to a zone of partial melt. And it's very consistent with previous study that showed that a deep, large silicic magma is likely present around 6 to 8 kilometers in the crust underneath the Taupo Volcanic Zone. And here, where you have the most recent magmatism, such as Taupo, that 6 kilometer is generally pretty low. One interesting thing that you can notice is this high intensity of seismic events along the margin here, likely the margin of the caldera. So the influence of the caldera margin in terms of fluid circulation is quite important. Another way as well of looking is using magnetotelluric, that some of my colleagues here, a paper from the ICE, looking at the resistivity signal underneath Rotorua and Waimangu. And as you can see, there is this, in most of the high temperature geothermal system that have been imaged, we are seeing those high rising plumb anomaly, conductive anomaly underneath the geothermal system. Underneath Rotorua, it's the anomaly is around, stop 2 kilometer, delineated again by seismic event, which are those black dots here. And they interpret this to be the top part and a saline brine with, I think, their model based on a 7 weight % NaCl equivalent, I think, something like that. And then you have a zone, a shallow intrusion. So this is what the geophysics tell us, that we can have some partial melt as shallow as 4.5 kilometer underneath Rotorua or underneath Rotokawa, but we also have a deep sitting high magmatism underneath some of the most active system. So, but where are we coming from? There is also, if we're looking at the geochemistry of those geothermal systems, it's been well known since Bernard Gegenbach that they have different type of composition in different function of where they're located. And he defined what they call the group B and a group A type. And the group A type, which is basically Oahu, Rotokawa, and Karo, are characterized by high CO2 and a low chlorine content, high boron chlorine ratio, high lithium cesium ratio, and a high nitrogen argon. And by similarity of this composition of those geothermal fluids with what is observed in a typical island volcanic arc in the Philippines or Indonesia, it was defined that those geothermal systems are likely related to arc degassing, and by analogy with some of the geological model at the time, defined that it was andesitic magmas feeding underneath the Taupo Volcanic Zone arc system, compared to the rest of it, which is most feeding by more rhyolitic basalt feeding rhyolitic magmatism. There is no an andesitic rift and a rhyolitic bulk arc right now in the TVZ. So we kind of need to merge together the geological model, which telling us that there is only a large proportion of rhyolite with very minimum, like not a real volcanic andesitic arc front in the TVZ, with what is observed in the geochemistry as well. So what we've been doing is trying to understand, based on whole rod geochemistry and over tracer, can we track down some of this magmatic degassing behavior in the current geothermal system? So if you're looking at what we know from geothermal system, and particularly where you have a supercritical fluid, you will have a magmatic intrusion at depths, and it could be located to 2 to 6 kilometers. This supercritical area that we obviously, some people that we've been talking, we're here to talk about. And then you have a conventional reservoir. We know, and Thomas defined that very nicely yesterday, that it's a continuity and there is a connection between the system. It's not a shallow conventional system and a deep supercritical system. There is a continuum between the two things. And there's a lot of reaction that happen in that area that we can try to track down. And most of them are defined by, and I'm not going to go in detail as Thomas in explaining all of the chemistry that can happen in this various points. But what we know is that when you have arc magmatism, andesitic or rhyolite, what we are most likely to have in the Taupo Volcanic Zone, those magma degas some complex, like some sulfur and some chlorine that can complex and transport metals, for example. And what we can track down the behavior in function of which pressure they are degassing and at which condition and which kind of composition. You will have some variability into the type of composition you will get above a magmatic system. And there's a lot of knowledge that we know from studying porphyry copper deposits. They are exactly the same kind of environment that is now that we are now able to explore and understand without necessarily the fluid chemistry, but we can understand how those large magmatic systems have been degassing. And what we're observing is that the volatile coming out of the magma generally leave above a chemical zoning and so a vector towards the magma. And when you have that is dependent on the complexation, the chlorine complex and the sulfur complexion, OH complex, and so all the ligands that are in the hydrothermal system. And so what you have generally is a zone enriched in copper, lead, zinc, or another zone, and above that a zone enriched in bismuth, tellurium, some antimony, and then close to the surface lithium toward this. So you have at the base more chlorine complex metal and chlorine ligand metal deposition, and then at the surface more sulfur and OH. So very simplified. But so what we try to do is using this knowledge that we have from ore deposits towards, so we try to use that in the Taupo Volcanic Zone. And luckily there is one system that we can use to understand what could be a degassing shallow intrusion in the TVZ. And in Natamariki geothermal field, There is a cold intrusion that is 0.5, 0.7 million years, and that this intrusion, when in a place, had a large proportion of magmatic volatile degassing and created a large hydrothermal halo around it. It's subeconomic. There's no, copper deposit, no gold deposit per se, but you can trace down the same metal anomaly above it. And so you have an enrichment in thallium around, then lead, zinc, bismuth, tellurium anomaly at a certain level above it, associated with certain pyrophyletic acidic alteration, and then toward the surface, all your sulfur complex metals such as gold, silver, some of the tin antimony as well. So we are able to compare this type of environment with the chemical vectoring that could be observed in our geothermal system to see, can we see the same thing in terms of trace, high detection trace metal anomaly. So we've sampled the deepest sample, like rocks and core cuttings and core sample, prefer working on core generally. We have more constraint on the depths and the mineralogy of the samples. The highest altered sample as well. Obviously, we avoid the samples that were not, that were fresh or fresh looking. And so we took some sample from Rotokawa and Hohaki, which are the two sites that were classified as fed by a shallow andesitic intrusion underneath the TVZ. This is one, for example, this is from Rotokawa. This is modified for my colleague Ted Bertrand. Magnetotelluric anomaly. So we have some sample at the in the art of the magnetotelluric anomaly at the top, not the art, I would say, at the top of magnetotelluric anomaly. So where we should be, there is some an intrusion at 4.5 kilometer or a zone of partial melt. Maybe we'll see some of this trace metal degassing. And so that's the result in what we observe. In green here, you can see the zoning with depth. So it's depth versus concentration. All the elements are reported in part per million, except for gold, which is in part per billion. In green here, you have the zoning associated with the fossil magmatic intrusion at Natamariki. In blue are samples from the Oaki geothermal field, and in red are the sample from Rotokawa geothermal field. What you are observing is this line here corresponds to the paleo surface of Natamariki. So all of the sample here, for example, this zoning in gold in the green sample is basically toward the surface. And without surprise, this has been shown by Stuart Simmons before, we have an enrichment in gold towards the surface, particularly in Hawaii. Rotokawa showed definitely less enrichment at depth, but there is a strong enrichment in gold toward the surface. Similarly, in arsenic, antimony, all the metals that are transported by sulfur, that are complexing with sulfur. Surprisingly, there is no silver anomaly for the active, for the present day geothermal system, but the Natamariki, the fossil zoning clearly show an anomaly in sulfur, in silver. One of the interesting things that you can compare here is that the magmatic hydrothermal transition show an anomaly in zinc, in lead, in tin, in bismuth, and tellurium. That is not observed in the active hydrothermal system currently. So, for example, here in bismuth, we can see that above the magmatic intrusion at Natamariki, we had this increase in bismuth concentration in the hydrothermal alteration, where like the geothermal system, that's not the case. Tellurium, and we're talking, 2 order of magnitude, 3 order of magnitude for some of the sample. So we clearly don't have the chemical zoning that we can see above a magmatic system. So what we're thinking, and this is some work that is submitted with John Dillis here, we are thinking that compared to a shallow magmatic intrusion, most of the heat source is likely we do not have a typical arc degassing shallow intrusion underneath the geothermal system, or certain the high gas typical arc composition geothermal system in the Taupo Volcanic Zone. The heat source has to come from deeper, or there's a high effect of dilution in those systems as well. And some of the chlorine can be come from some recycled water rock interaction. So obviously we have deep CO2, we have deep nitrogen coming from greater depths that are likely fed by the mush, but we do not have the shallow magmatic intrusion type underneath some of the most active geothermal system in the Taupo Volcanic Zone, based on the chemistry. Another way of looking at some of the variation we have is looking at fluid inclusion, and obviously at Natamariki above the magmatic-hydrothermal transition, and similarly to what is observed in any quartz vein close, like in a system relatively shallow above a fossil magmatic intrusion, you have multi-phase hypersaline, saline, brine with multiple salt fluid inclusion that exists, where like obviously in Hawaii and Rochikawa, except some clartet, sometimes you have a boiling assemblage or single phase fluid inclusion. And in term, and those fluids are generally both fluids are generally low in salinity, so the single phase two-phase liquid vapor are generally maximum salinity of 2-3 weight percent sodium equivalent NaCl equivalent, where like in Natamariki, in those high hypersaline brine, you're reaching some very high salinity for those magmatic fluids, which is very well known and is very similar to what is observed in fossil hydrothermal system, magmatic hydrothermal system. In terms of composition, we can trace down as well the trace elements content, and there's some clear variation. You can see that here in red, green, and the stars are so fluid inclusion trap from rhyolitic magmatic in quartz phenocryst in the tonalite intrusion and Natamariki. Both are from a diorite intrusion trap in the wispy quartz vein in the diorite intrusion, and this is the so-called vein above the magmatic intrusion. So we can clearly see a zoning in metal content. They are generally very enriched with high concentration in gold and silver, and concentration in lead and zinc as well. One interesting thing is that if you're comparing with the triangle symbols, which are the composition of the fluid inclusion in active hydrothermal systems at Oaxaca and Rochikawa today, we can see that they are depleted in potassium. No gold or silver were actually, unfortunately, able to be analyzed in the fluid inclusion, but it's compared to some of the data that exist on the fluid composition, we're generally depleted compared to the others. And another interesting thing as well is that we have this. They are highly rich in cesium, but generally depleted in zinc and other metals compared to a typical magmatic hydrothermal system, which is expected. One interesting thing as well is that we are able to compare the fluid inclusion to the normal geothermal well classification that we have, like compared to lithium cesium or boron chlorine, and our fluid inclusions here for example, the Oaxaca composition, which are those diagrams, are in the same range than the geothermal fluid composition. So we're pretty confident about the composition of those fluid inclusion that are reflecting actually the composition of the geothermal system, the present day geothermal system, and the fluids that are circulating through it. And there we show again this high boron chlorine zonation that you have that was observed at Oaxaca. But compared to the typical magmatic hydrothermal system that are a lot richer in a huge variation in lithium cesium, we don't have this enrichment in boron in both magmatic-hydrothermal fluid. So most of this boron chlorine is due to water-rock interaction with the basement than magmatic degassing. So what next? So all of those geological, and there's a lot more that we are doing in this space, but there's some limitation to geochemistry and geothermal system because we like on samples, fluid sample, because we do not have access to the supercritical condition. So that's why we're trying to give the modelers, in particular Thierry and Thierry Solms and Thomas at Zurich, to give them, and Thomas mentioned that yesterday, as much as possible constraint on the geology, the geochemistry, and the geophysics of the system, so they can really model as accurately as possible with the limitation of the, obviously the thermodynamic limitation that Thomas explained this morning. But we're also looking with Laura at Vic, we're also looking at what is the status of a deep mush. As because we can understand and we have a good understanding of what can happen if we have a shallow intrusion, it's really harder to understand what are the chemical phase and the variation that can exist in the quartzo-feldspatic, the granitic crust. There's so much magma that is wrapped in the TVZ that there's probably a large amount of granite that also crystallize at depths in the Taupo Volcanic Zone. And knowing how those granites behave and how the chemistry of the fluid that may be trapped when get crystallized, it's really unknown now. So we are looking on that side as well. Just a brief thing about GNG, which is there's a collaboration between different groups. So I just wanted to acknowledge that. But if you want more detail on all of the research that is happening right now in New Zealand, please visit the go on the geothermalnextgeneration.com website. It's a great website. That's where we're putting updates, and we're putting a lot of as soon as we're having a paper or we're having a proceeding, we're trying to do a lot on that site. So please don't hesitate to check it out. And that will be all from me.